Welcome. In this video, we are going to talk about pH and what pH represents mathematically. Like, what does that number tell us? So first what we're going to do is we're going to take a look at this data table. So we got a set of information, and we notice we've got some HCl solutions. And HCl is an acid. Remember, one way to recognize an acid is that they tend to begin with a hydrogen. So that's an acid, and we see we've got different molarities and different pH values, and then we have these molarities also written in what we call scientific notation. So we want to take a look at this and see if we notice some patterns here. So a pattern that I notice as I look at this data set is I go from row to row. Notice how the concentration of the acid is decreasing by tenfold. So it goes from 1 to 0.1 to 0.01 to 0.001. And as it does that, the pH increases by 1. So as the acid concentration decreases by 10, the pH increases by 1. So if I were to follow that pattern, if I had a solution of 0.00001 molar, what do you think the pH would be? So notice how this is 0.0001. So this one has an additional 0. I could also write this as, let's see, 1 times 10 to the 1, 2, 3, 4, 5, 1 times 10 to the negative fifth molarity HCl. That's how we write that in scientific notation. And following this pattern, I would predict that the pH would be 5. So each time the concentration changes by 10, the pH changes by 1 unit. And then if I had a solution with a pH of 6, again, following this pattern, if the pH were 6, then I guess that the hydrogen concentration would be 1 times 10 to the negative 6. If I wanted to write that out in what we call standard notation, that means you take your 1 and then you move this 1, 2, 3, 4, 5, 6 spots over. So that's 0.000001 molar. So that's a pattern we're noticing, and we call this a logarithmic scale. Logarithmic. That means that every time the pH changes by 1 unit, the concentration is changing by 10. There's some things to be aware of with notation. So one thing to be aware of is we often use square brackets in chemistry to signify concentration. So instead of saying the hydrogen ion concentration is 1 molar, we might just say H plus is 1 molar. So the square brackets here represent the concentration of. So instead of writing the words, the concentration of, we can just use square brackets instead, and that's what those mean. So I want to be aware of that. Square brackets mean concentration in molarity. And then we also want to be familiar with scientific notation. So it's a way of taking, it's a useful way of taking really big or really small numbers and writing them in a way that's a little bit kind of easier to see. So we're going to deal with a lot of examples of negative exponents here. So if you see a negative exponent like 7.6 times 10 to the negative 4, what that means, if I were trying to convert that into what we call standard notation, is I take this 7.6 and I move the decimal 1, 2, 3, 4 spots over. So 7.6 times 10 to the negative 4 is the same as 0.00076. And they're both correct ways of writing this number. Sometimes it's more useful for us when talking about pH to look at the scientific notation version of it. Sometimes you'll find that more helpful. So here's just some practice with scientific notation. So it looks like this number is 2.0 times 10 to the negative 2, because see, I moved my decimal 2 spots over. I kind of like to count it out there. This number is 5.3, and the decimals moved 1, 2, 3, 4 spots over. We also could write this as 53 times 10 to the negative fifth, but we don't usually do it this way. When we do scientific notation, we want just 1 digit to the left of the decimal. So we want a number to be like in the ones place. Here's just what we're going to convert the other way. 6 times 10 to the negative 5. So I'm going to take that 6 and I'm going to move it 1, 2, 3, 4, 5 spots over. So that's 0.00006 molar. And then this I'm going to take it and move it 8 spots over. That's a lot. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that's a little bit about scientific notation. And then again, square brackets means molarity. So with these patterns that we notice, we want to fill in the blanks in this table below. So notice if something is 1.0 molar hydrogen ions, in scientific notation, we could write that as 1 times 10 to the 0. And notice how the pH is 0. And remember how we started noticing some patterns here, right? That as the concentration changes by 10, the pH changes by 1. And you may also have noticed that the pH matches the exponent. We didn't mention that earlier, but this pH matches this exponent value. So if this is a 3, that's a 3. This is a 4, that's a 4. So we want to use that pattern to make some predictions here. So notice how if this is a 0, the pH is 0. So in this number, if this is a 1, that means our pH is going to be 1. And then when our pH is 3, notice how the scientific notation is of this value would be 1.0 times 10 to the negative 3, and the pH is 3. Okay. Down here, 1 times 10 to the negative 6, the pH is going to be 6. If I write that in standard notation, it's 1, 2, 3, 4, 5, 6 molar. This one, the pH is 7. If I look at this, it's 1, 2, 3, 4, 5, 6, 7. It's 1 times 10 to the negative 7. So we should notice again that the exponent in the hydrogen ion concentration matches the pH. So that's why it's nice to sometimes write out these numbers in scientific notation rather than just standard notation, is it will allow us to maybe see the pH a little bit easier, because that exponent in the concentration is what tells us the pH. And then and then let's start filling in acid, base, or neutral. So we know that acids have pH below 7. So these first ones we're looking at, this one's acidic. Neutral is when you have a pH of 7. Okay, so this would have also be 10 to the negative 7. And this would be 0.1, 2, 3, 4, 5, 6, 7. There we go. Let's see, salt water. Let's check this. 1, 2, 3, 4, 5, 6, 7. All right, salt water is also neutral. It's got a pH of 7, and the concentration is 1 times 10 to the negative 7. So this is also neutral. And then we're starting to get in some things that are bases. Washing soda. That's really similar to baking soda, just so you know. It has a pH of 8. Notice how the concentration is 1 times 10 to the negative 8. If I write out in standard notation, that's 1, 2, 3, 4, 5, 6, 7, 8. There we go. Ammonia, 1 times 10 to the negative 10. So it has a pH of 10. It is also a base. Drain cleaner has a pH of 13. So that's a 1 times 10 to the negative 13. It is also a base. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Ooh, that took a while to write out. Okay, and then our last one, if you have 1 molar NaOH, that's about the highest pH you can get. There's also a base, and then that's just one more 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, whew. There we go. So with this pattern, one other kind of general pattern you want to notice, as the pH increases, the hydrogen ion concentration decreases. And as the pH decreases, the hydrogen ion concentration increases. So we want to notice it as an inverse relationship here. So a solution with a higher pH has a lower hydrogen ion concentration, and a solution with a lower pH has a higher hydrogen ion concentration. All right, so let's think about making some comparison statements. Let's say you have two solutions, one with a pH of 5 and one with a pH of 9. Think about those patterns that we just talked about. Solution A, if it has a pH of 5, that means its hydrogen concentration is 1 times 10 to the negative 5th. Solution B has a pH of 9. That means its concentration is 1 times 10 to the negative 9. So which of these is larger? Well, pH 5, because it's a negative exponent here, so 1 times 10 to the negative 5th, that's 1, 2, 3, 4, 5. That is a bigger number than 1 times 10 to the negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just writing it out this way in case that makes it easier for you to visualize what I'm talking about here. All right, so pH 5 has a greater concentration, and then let's quantify that. So how much greater is that? Well, let's take these two numbers. So 1, 2, 3, 4, 5 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can actually stop, and plug these numbers into your calculator. I should say another way that you can type this in is if you want to type in 1 times 10 to the negative 5 in your calculator, you can type in 1, and then you probably have this button that says E, or it might be like a double E that looks like that. So if you want to try typing in your calculator that way, this exponent button is very useful to find. Depending on what calculator you have, it might use it might look like that, EXP. So talk to me if you want to use that, button and you are not sure where it is on your calculator. But when I divide this, it is, oops, I put my comma in the wrong spot. This is 10,000 times more concentrated. So if something has a pH of 5 versus a pH of 9, remember, since this is a logarithmic scale, each change in pH is a 10-fold change in concentration. So if the pH is, when you're comparing these two pHs, let's write it this way, 9 minus 5, it's 4 pH units difference, but each pH unit represents a factor of 10. So it's basically 10 to the 4th more concentrated. So 10 to the 4th is, is 10,000 there. So it's way more concentrated. So just keep in mind, pH is logarithmic. All right, some more practice down here. So standard notation, scientific notation, the pH is 2. It is an acid. 7, that is neutral. So it's got the scientific notation would be 1 times 10 to the negative 7. Standard notation is 0.1, 2, 3, 4, 5, 6, 7. 9, this one here, it's a base, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I have to count out loud, otherwise I lose track. Okay, so you get the idea. Try the rest here. And then here's a visual summary looking at the relationship between hydrogen ion concentration and the pH scale. This is an excerpt from a reading. And then if you were wondering, well, what if the concentration isn't exactly 0.1 or 0.01 or 0.001? We know we often deal with solutions in different concentrations. Well, we actually have a formula here that we can write this relationship that we've been using so far as a mathematical formula. And the formula is this. pH is the negative log of the hydrogen ion concentration. This is how we write out what we call a logarithmic relationship. And so what you can do then, if you plug this in your calculator, okay, so pH is the negative log of the hydrogen ion concentration. Let's say the solution is 0.1 molar. If you take the log, so try this in your calculator right now, find the log button, and then do log of 0.1, you will find that the pH is 1. So when the concentration is 0.1, the pH is going to be 1. So we've been kind of using this relationship without really even realizing it. But this actual mathematical formula is useful if you're dealing with molarities that are not, exactly, where there's not a 1 there in the front. Okay. So for example, what if the solution is 0.5 molar hydrochloric acid? Well, to find the pH of that, you would take the negative log of the concentration of 0.5. So I just have a few practice problems in here where all we're doing is just plugging things into our calculator. And that's the pH is going to be 0.3. So your pH is actually going to be less than 1. And that can happen. pH can be less than 1. pH can actually be negative. We have some solutions that actually have negative pHs. That is possible. Not super common, but it is possible. Okay, let's try this one. You take the negative log of the acid concentration. That's 0.028. So you can just plug this in your calculator. Find where that log button is. Okay, that's 1.55. And then this last one, the negative log of 0.123. There we go. Log 0.003. That is 2.52. All right, so there we go. Hope that helps. Thanks for watching.